Namaskar. In today's lecture for the microwave electronics paper for the chapter of two cavity Klystron, today we discuss the current modulation in the two cavity Klystron. In our previous lecture, we have discussed the construction and design of the two cavity Klystron, and also we have obtained the expressions for the velocity modulation and the bunching process. Before calculating the current modulation equation, again we will briefly discuss the construction of the two cavity Klystron. In the figure, we have shown two cavities named as the buncher cavity and the catcher cavity named as R1 and R2. A small signal RF field is given to the buncher cavity and RF output signal is obtained from the catcher cavity. From the electron gun, the electrons are emitted, and after that they were accelerated by the DC potential applied between cathode and anode, and we are assuming that all the electrons emitted from the surface of the cathode and after acceleration they all have the uniform velocity v0 before reaching the grids of the buncher cavity. The first cavity grids are named as G1 and G2, and due to the application of the small RF input signal between these grids, the steady electron beam which passes through the cavity grids G1, G2, due to the alternating potential between G1 and G2, there will be a change in the velocity of the electrons, and the electron velocity after come out from the buncher cavity grids will be a function of time, and therefore we can say that the velocity modulation takes place. And after that these electrons pass through the drift space between the buncher cavity and the catcher cavity. Now when the electron beam is passed through the catcher cavity grids, the distance capital L between these two cavities is optimized so that each electron cluster after bunching process when passes through the cavity grids G1, G3, G4, that will be retarded. Means the electron bunch when passes through the grids G1, G3 and G4, the field between the grids is such that the electron bunch will be retarded and it will lose its energy to the cavity grids. The kinetic energy imparted to the field will be converted into the electromagnetic field, which will produce a AC current component to the oscillating field, and when the current induced in the valves will be in the same phase of the current which already exists due to the excitation of the catcher cavity, it will induces an amplitude, and hence we can say that the current modulation takes place. The remaining electrons after losing its energy, and when passes through the catcher cavity grids, they will be finally collected by this collector electrode and the walls of the tube. Here we will also assume that electrons entering the grids at time t1, they will pass through the grid G2 at time t1 plus tau, means tau is the transit time required in crossing the grids, and after that these electron bunches will pass through the catcher cavity grids at some later time. Z is the direction of the propagation of the electron trajectories along the beam. Now we will calculate the current flow represented by the bunched electron beam as a function of time and distance along the beam under the same assumptions: V1 very less than V0, where V1 is the amplitude of the AC field employed between G1 G2 grids of the buncher cavity, and capital V0 is the DC potential applied between cathode and anode. And again we are assuming the condition that the mutual repulsion between the electrons is neglected here. Now the time for the electrons to pass from gap R1 at time t1 and along the beam at any time t2, then t2 minus t1 will be given by Z over V, where V is the velocity after the velocity modulation process already discussed in our previous lectures. From this equation, the time t2 may be calculated and is shown in this equation. Now we will follow the method of analysis, and we will consider a small quantity of charge dq at its two locations, once at the first cavity grid, which is at distance z equal to 0 and time t equal to t1, and at the later time interval at any distance z along the beam and at later time t2. So by the conservation of charge principle, dq at 0 t1 must be equal to dq at 0 t2, but we also know that dq is equal to I dt, where I is the beam current. So therefore at these two locations of the charge, we can write down the equation I1 dt1 equal to I2 dt2, where I2 is the current beam at ZT2. Later we will consider it at the catcher cavity grids, and I1 is the beam current at the first gap, which is equal to I0, that is the DC or anode current. So therefore we will have the equation I1 dt1 equal to I2 dt2, or from which the current I2 is given by I0 into dt1 over dt2. Now from the previous equation, time t2 is given by z root m upon twice q v0 into 1 minus k v1 over twice v0 e raised to the power j omega t1 plus t1, and From this equation, when we differentiate it, it will gives us dt2 over dt1 by the differentiation of the above equation. It will gives us minus z root m upon twice q v0 into k v1 upon twice v0 into j omega e raised to the power j omega t1 plus 1, and therefore we will solve it to find out the value of dt1 over dt2, which comes out to be equal to 1 minus jm e raised to the power j omega t1 power minus 1. Here m is called the bunching parameter and is given by m equal to omega kz under root m over 8q into v1 upon v0 power 3 by 2. So this equation will gives us the value of I2 equal to I0 into 1 minus jm e raised to the power j omega t1 power minus 1. So in calculating the current I2, we will also consider the contribution from all the electrons which left the Buncher cavity grids at different instances of time t1. So therefore, summing up all these contributions to the current I2, then this gives us I2 equal to I0 and sigma n 1 plus m sine omega t1 power minus 1, where only the real part in the above equation is retained here. So clearly this equation, when we expand the right hand side, it will gives us the contributions from several harmonics, and therefore a Fourier expansion may be supposed. So this equation I2 for I2, this will gives us the current as a function of time, and due to the presence of sine omega t1, sine twice omega t1, etc., it means this current is a pulsed current, and if we plot I2 over I0 versus time t2, this will gives us the pulsating current graph for different values of the bunching parameter m. So it is also interesting that if m equal to 0, for which there is a straight line plot, means the I2 upon I0 will be unity, and or I2 equal to I0 means there is no pulsating current. For m equal to 0, if there is no bunching, then the current will be the DC anode current, and for other values of m, for example m equal to 0.50, m equal to 1.841, m equal to 1, m equal to 3.82. If we consider, then these several pulsating components for the various values of m, these are shown in the figures. So clearly the anode current will be a pulsating current. So from these typical graphs, it is clear that the output current will contain all the harmonics. So therefore a Fourier expansion at time t2 may be written, which is given by I2 equal to sigma n a n e raised to the power j n omega t2. So here a n is the component of the beam currents corresponding to the different harmonics. Here we are interested only in the fundamental component A1 of the pulsating current, because the fundamental current component will have its dominant effect over the other components. So to find out the fundamental component of the beam current, that is A1, we will multiply both sides of this equation by e raised to the power minus j omega t2, and then we will integrate it for the one complete cycle, that is between the time limits 0 to capital T. Now on the right hand side, the only term which we obtain is for n equal to 1, and all the other remaining components for different values of n will be 0. Now to solve the integration for the left hand side, first we will find out omega t2 from the previous equation of t2 in terms of t1, and changing the third term on the right hand side in terms of m, which is the bunching parameter as already discussed. And also if we consider omega t1 equal to 5, and if we write down it for the real part only, then omega t2 equation will comes out to be equal to 5 plus omega z over v0 minus m cos phi. Also using our previous relation, that is I2 dt2 equal to I1 dt1, or it is equal to I0 dt1. So now we will solve this above integration equation between 0 to t. I2 dt2 is replaced here by I0 dt1, and for omega t2 using this relation omega for omega t2 as already we have shown, and when we will simplify this integration, then the value of the fundamental component A1 can be obtained in terms of I0 upon omega t e raised to the power minus j omega z over v0, and integration between 0 to 2 pi e raised to the power j m cos phi minus 1. Omega t equal to 2 pi, here it is used, and the integral on the right hand side of this equation will yields a value minus 4 pi j j1m, where j1 m is the first order Bessel function of argument m, and hence the value for a1 is obtained as a1 equal to minus twice j I0 e raised to the power minus omega z over v0 into j1m, and in this equation the exponent term minus j omega z over v0 is the phase factor corresponding to the time delay for the electron beam travel through a distance z from the first resonator, that is R1. The fundamental component of the beam current is thus obtained. Later we will use this equation to find out the power output and the efficiency of the 250 Klystron. Now considering m equal to 1.841 value, for which the Bessel function j1m will have its maximum value. So for the maximum component of the fundamental beam current A1, the value of M here is considered to be 1.841, and we will equate this value equal to omega k z over V0 into V1 upon twice V0. So this distance z at which the maximum fundamental component of the current occurs, this will gives us the value of z, which comes out to be 3.682 V0 upon omega into capital V0 over V1, taking beam coupling coefficient k equal to unity. So if we now compare this result of z with the earlier obtained value in our previous lecture for the distance at which the bunching will take place, that is when the electron trajectory converges to bunching. This equation for z have its value z equal to pi small v0 upon omega into v0 upon v1. So if we compare these two results for the z, so this latter result is almost 15% lesser value as compared to the previous one. So the discrepancy in between these two results is due to the several approximations which we have used and in obtaining the results. So here one of the assumption is that the fundamental here we have considered only the fundamental component of the beam current, which is not only the one factor but the total current, total pulsating current will have other components for the higher harmonics, although their amplitudes are small as compared to the fundamental beam current, and also the other assumptions which we have assumed, that is V1 very less than V0, and also the mutual repulsion between the electron trajectories is neglected. So both the results are almost same, and under the assumptions which we have assumed, so the results are in agreement with each other. So at this location of z, at this value, here we will find out the maximum AC beam current, and in our next lecture we will discuss that at this location z, if a second cavity, which is called the catcher cavity, is placed at this optimized distance and the field between the cavity grids is maintained, so that the bunches or clusters of the electrons will be retarded, then the energy loss in the kinetic energy of the electron bunches will be imparted to the fields of the second resonator cavity, which will be converted into the AC fields in terms of the generation of the microwaves. Thank you.